Greetings, this is Artie from Artifact Electronics. In this episode, we're going to do some troubleshooting on this Star Trek The Next Generation pinball. I got this machine a while ago. I've owned one of these many years ago, and like so many other machines, stupidly sold it, expecting to be able to replace it quickly. And at that time, this wasn't an unreasonable thing to assume, because there were a lot of machines out there. You'd sell one of these and 2 weeks later another one would show up and you'd buy it. But as I was selling these machines, the supply kind of went away. And I've had a hard time being able to replace it. But anyway, I was able to replace this one. It's in beautiful shape cosmetically, but it has a lot of mechanical, or had a lot of mechanical and electrical problems. I fixed these, and originally I wasn't going to do a video on it because most of the problems in it were very common and not very interesting to fix. Stuff we've looked at before. Broken solenoid mechanisms, dangling wires. The machine wasn't maintained. It was sitting in a home for 18 years, which is an excellent thing, which is why it's in such great shape cosmetically, but the machine just degraded inside as it was played. But the reason I am going to recreate one of the repairs, or a series of repairs, is it was a little bit out of the ordinary what the solution was, and I think you might be interested in following along and seeing how I found the problem. Now, first a disclaimer, I'm not a big Star Trek fan, so I'm not a member of the hordes of Trekkies. I mean, I like the show, but it never was something that overly excited me. But this game's really great, and a little bit of knowledge of the show makes it that much more enjoyable. I mean, look at the toys on this thing. We have a Borg ship here that lights up. The Romulan bird. We got the shuttle. There's just lots of stuff here. Look at these ramps. When you feed the ball, it goes up this long ramp and then loops around and gets fed up into the top of the playfield over there. So yeah, it plays even nicer than it looks. One of the big features is it's got two guns, and the guns come into play. They get fed balls, feed into the guns, and then they start rotating, and you shoot at different things on the playfield by triggering the gun, and it's a great experience. So but it had a lot of problems, as I mentioned, and I was going through fixing things. And what really had me stumped for a while was switch problems. On a pinball machine, all the input to the CPU comes from various switches strewn across the playfield, both above and below, and that tells the computer where the ball is, what you're doing, and sequences the game. So if the switches don't work right, or give false information, playing a game on something like this is not very enjoyable. And this machine had some severe switch problems. Let's have a look at some of the switches that are above the playfield, or visible from above the playfield. The most common ones are these stand-up targets over here. They're basically leaf switches. And, well, she wants to be played, I guess. But that's basically two leaves, and when you hit the plastic part with a ball, it completes the circuit. And that's the most simple kind. The next kind is a micro switch that usually has a lever here. When the ball goes through, it triggers that switch, This machine also has eddy sensors, which are mounted underneath the playfield over here. And eddy sensors basically are driven by magnetism, and when a steel ball passes over them, it reports a switch closure. And finally, the part that gave me the most grief, I don't know how well I can show this from above, but are opto-interrupters. And you can kind of see an opto-interrupter built into the gun here. It's got a transmitter, an LED, an IR LED, and a receiver, a phototransistor. And if there's no ball in here, the LED shines on the phototransistor and basically outputs a 1. When the ball goes in here, it interrupts the beam. Now look at that. So the reason it did that was it thought there was a ball in there, and it tried to kick it out. But as I was saying, so when there's a ball in there, the beam is interrupted and the output goes to 0. So this has got active low circuitry on the optos. A 0 means that the beam is interrupted, which translates to a switch closure. And if you thought there was a lot on top of the playfield, get a load of this. Here's what the underneath looks like. It's got all of these subway ramps underneath that when the ball falls into a hole on the playfield, it goes through these, but the machine decides where the ball ends up. So if a ball gets shot into here, it rolls through here, comes up here, and then the machine decides whether the ball should go left or right. And there you go. There's a diverter here that'll pull in and guide the ball either left or right. Then there's storage spaces, or so-called ball troughs, that can hold several balls. They're up kickers that will feed them back into the game. There's another one on the other side. And the most important ball trough in here is the regular ball trough up there that can hold up to 6 balls, and that's where the balls get kicked in for play. And that's where the problems started. And for completeness, of course, we have the pop bumper assemblies over here, several of which were defective. There's a drop target over here that is kind of hidden from view, but the drop target can either be raised or lowered by the computer. There's another diverter coil over there that when you're shooting it up one of the side ramps, the ball either goes into the Borg ship or across the playfield on another ramp. So looking at the stuff, I mean the continuity of how this works and how the ball is moved around, there's no big mystery here. Let's see, what haven't we talked about? Oh, here we have one of the eddy sensors. This is the PCB, and this is where the actual sensor is underneath the playfield. And maybe a little better view. Now we got the light in there of the ball trough, but the ball trough is where we start. So this is where the balls drain into, and underneath there sits the ball trough, which you can see, kind of see from here. And the ball trough is just that. It's a trough that'll hold up to 6 balls, and the way it detects balls is it has opto-isolators in it. This board over here, which we'll take out in a minute, has 6 transmitters, which are just IR LEDs. And a similar board opposite has 6 phototransistors that are sensitive to the wavelength of the transmitters. So when there's a ball in there, it interrupts the beam, and we know that there's a ball there, and there's 6 positions, so the machine will always know how many balls are sitting in the ball trough. And that's very important because it has, in order to manage multi-balls and feeding extra balls into the game and so on, that gives the machine a good representation of where the physical items are. The first problem, which is actually quite common for machines of this era, this is in 1993, is you're starting a game and the game starts out by kicking out a ball, and then all of a sudden it'll kick out a second ball or a third ball. So there'll be like 3 balls in play. This also has an auto launcher, so when a ball gets fed into here, it gets kicked into the playfield. So all of a sudden you got 3 balls in the playfield, and the machine just gets confused because it thinks there has to be 1 ball. So say you have 3 balls on the playfield when there's supposed to be 1, and one of them drains. The machine starts playing the ball over tune and wants to shut down and go to the next ball. And then it detects that there's still more balls on the playfield, and things get really, really confusing. So I removed the transmitter board. There's the, over here is a red LED. That's always visible. But the trick here is that, keep in mind, these are IR LEDs. And with the naked eye, you cannot see them light up. But a lot of digital cameras do pick them up and make them visible. So just looking at all the LEDs, I mean, just imagine these being off if you're looking at them with the naked eye, but through a digital camera, you can clearly see if they're lit up or not. And when I first checked this, 2 of them weren't lit up. Well, what that means is that those positions, the machine always assumed that there was a ball in those positions, and it would just happily start kicking out balls trying to fix that situation. And I don't know how the logic works, but I mean, if we say that this LED is off and this LED is off, but this one's on, saying that there's a ball here, but there's no ball here. So the machine assumes that there's some sort of obstruction in here that's keeping the ball in this position moving to this position. And so by kicking out balls, it hopes to fix that situation. Well, if it's a defect with the LEDs, obviously that won't, and that causes extra balls to be kicked into the playfield. Whenever removing boards like this, make sure to turn off power to the machine. The reason for that is, see that solenoid here? And this solenoid is what kicks the ball up into the playfield. That solenoid's got 75 volts sitting on the lugs. If you pull this board out of here and you accidentally touch that lug, you will wreak havoc with the switch matrix. So taking this board out, or taking anything out that is near a solenoid, turn off the machine. Some people they're too lazy to do it, they don't want the machine to have to reboot the machine, but take it from someone who's been burned by this. Turn off the machine when there's a possibility of a low voltage PCB touching a high voltage lug on a solenoid. Anyway, the aforementioned solenoid causes a lot of shock over here when it pulls in. What that does is those current limiting resistors on the transmitter board, they have some mass to them, and what it causes is the solder joints break. They break or they crack, And if the limiting resistor doesn't make good contact, it doesn't light up the transmitter, and so the opto will never ever work. So the aforementioned problem of the machine kicking out balls randomly was very easily solved by reflowing all of the solder connections for the resistors. While you're at it, you may also check the resistors for proper value. They run them pretty hot in these machines, but the resistors were all good. It just had cracked solder joints, and the cracked solder joint basically made it intermittent, because whenever the solenoid pulled in, the leads would wiggle in the cracks and cause all sorts of weird situations. But that was a quick fix. After resoldering that, while I was at it, I resoldered the header connections, just reflowed it, did the same thing for the board on the other side of the trough, which looks kind of the same, but instead of having the LEDs, it has the phototransistors, which look exactly like the LEDs. So that part was solved easily, and there were no more extra balls getting kicked out of the main ball trough. A more long-term solution to this problem could be shock mounting these boards. I mean, these are screwed directly to the metal trough, which transmits all of the solenoid shocks directly to the boards. And what's been suggested is to enlarge these holes, put rubber grommets in there, so when you screw them in, they are not rigidly attached to the trough anymore, I mean the PCBs, but rather are now shock mounted and reduce the shock of the solenoids and thus prevent cracking of the actual joints. I'm probably not going to do that because this is a home machine and it doesn't get used that much. But if you're using this commercially, it's probably a good idea to do that. Other machines that suffer from the exact same problem most prominently include the Indiana Jones machine, which also has pretty bad trough problems. But if you know, since the problem really isn't that bad, I mean that bad to diagnose, you just got to resolder everything, and if it keeps happening, then shock mount it, and you should be done for life. At this point, I think a diagram is in order because keep talking about the optos. We're going to be talking about them a little more. So here's what the optos look like. An opto circuit looks like electrically in a simplified fashion. We have the transmitters, just an IR LED, physical space in here, and then the receiver, which is a phototransistor sensitive to the wavelength that this emits. And then the output of the transistor runs through a comparator and gives a 0 for when it's blocked and a 1 when it's open. And the way it works is, in the normal circumstances, this is shining on this, the base is closed, connecting V plus to this comparator input, and it gives the appropriate output. There's a ball in here or some other obstruction. I mean, it's not just balls that can interrupt the opto, but mechanical assemblies and stuff like that. So when it's closed, then it's not getting any light, and it's blocked. There's no voltage coming through here, and it indicates such. So that's how they work. And here's what the LED looks like. I bought a bunch of these because I'll explain later why, other than just having parts. But yeah, it looks like a regular LED, but of course it emits infrared light. And then the receiver looks just like an LED, except the color of the case is dark to filter out stuff. And these face each other in some way, shape, or form in whatever assembly they're in, and when something goes in between them, it detects that as a switch closure or switch opening. So now you should have a better idea of how these things are supposed to work. And let's get back to the machine and look at the cascading problems of switch detection. So after fixing up the ball trough, I thought, okay, now we can actually play a game. And yeah, game started, kicked out one ball, but machine behavior was very erratic, to put it mildly. And at first I didn't know what was happening. I mean, the ball was going around, triggering all sorts of switches, unrelated switches to where the ball was. And finally I narrowed it down to the point where, for instance, this target over here, when this was hit, it detected that this specific target was hit. But it also thought at the same time that there was a ball just being shot in here, and it also acted like, okay, you hit both that switch, the stand-up target, and you shot a ball up this hole. So now I knew I was acting erratic because a lot of these stand-up switches on that side, and some other switches actually double triggered, meaning they triggered themselves and some unrelated switch. I looked at the switch matrix and tried to find some sort of correspondence between why certain switches triggered others, but I couldn't find anything. Another funny thing was, as I mentioned before, you hit this switch and it triggered this hole over here. But if I rolled a ball into this hole, it did not trigger this switch. So at that point, yeah, I was a bit stumped at that point because I couldn't find a logical explanation for it. But when you're dealing with switch matrices, any short in a switch matrix, like if one of the diodes shorts or a wire touches a ground somewhere, it will result in really erratic behavior. It is unpredictable, and switches will trigger. A certain switch will trigger other switches, but not the other way around, and it's just some really weird behavior. And what that means is, yes, there is a physical short somewhere or a bad diode. So we had to go and find that. You can see that every switch has a blocking diode on it because it's part of the matrix. And somewhere there is a bad diode, or something's touching something it shouldn't. And from the top of the playfield it doesn't look too bad, but it does become a daunting task when looking at the underneath of the playfield. Considering that we have an 8x8 matrix which supports 64 different switches, but there's also an extra column because they ran out of switches, I guess, and they added an extra column. So we actually have a total of 72 cross points in the switch matrix. And it looked like I'd have to get out the meter and start measuring diodes and see, what could be causing all of this good stuff over here. But then I remembered when I first got the machine, the drop target wasn't getting detected. And the drop target has a switch right here that pretty much tells us when it's up, the switch is open, as you can see from this blade here, and when you let it down, the blade comes down and it closes it. Now this whole bracket, it keeps saying that when I hit the flipper button accidentally, but this whole bracket was bent out as if somebody tried to disable this switch or there was a problem with it. And I bent the bracket back and it started somewhat detecting the drop target position. It still wasn't working very well, but at least now it knew most of the time where the drop target was. And as I'm starting to measure diodes, I noticed, if you look at the switch connections over here, we have the white wire going to the top and the green wire going to the middle of the switch. And after staring at it, I finally saw that this white wire, this white violet or white brown wire, wasn't connected over here, but rather connected to the other side of the diode. So what that means, it essentially shorted that diode in the switch matrix. So somebody did a really good job of fixing it. I think somebody replaced that switch. They soldered the wire on wrong, and when they saw that it was creating all sorts of problems, they figured, hey, let's just bend the bracket, and maybe that'll fix it, and then just left it that way. So that was a huge problem, because that was our short in the switch matrix that a repair person had introduced. Moving that wire to the proper position at the other end of the diode got rid of all of the double triggering, and now I was really ready to play a game. But still, not all was well. I could play a much more normal game, but it would start kicking out balls again, but not from the main ball trough, but rather from these troughs that feed the cannons on both sides. And so you'd say, hey, fix it like you fixed the ball trough, except the way these work is they only got the diodes mounted because there's several of them, and I guess there wasn't enough room to put a PCB on there, so they got the diodes are all on their respective mechanical assemblies, like there, or like in the guns as you saw earlier, in the muzzle of the gun there's an opto, but there's no driver electronics. So what they did was, there is a driver board for the remaining optos, which is that board over there. It's called a 16 opto driver board, and you run the opto terminals directly to this board, and it reports about the state of 16 different optos. As you can see, it's got the same resistors on there, and it's got the comparators on there. Everything is there, and it just outputs the information to the switch matrix. So again, hey, that looks simple, right? Take out that board and reflow everything. Well, I took out the board, I looked at it, and I could not find any defects. Now see, that board is not mounted on the same assembly as the solenoids, so it doesn't get mechanical shocks all the time, and just as I expected, everything looked good on it. I still went ahead and reflowed all of the resistors. I reflowed the connectors for the headers, and I also shorted the inputs, simulating opto closures and openings to see if the comparators over here were maybe misbehaving. But they all worked right. And without a whole lot of hope, I started up another game, and that hadn't made a single difference. You get into a special mode, the guns are getting loaded, the side ramp is getting loaded from these ball troughs, and again, there was no rhyme or reason to it. So what could be causing this? I put it into switch test, which makes a beeping sound whenever a switch closed. Started rattling the playfield, introducing shock. Nothing seemed to mistrigger. But the minute you start playing a game, things went bad. And this was a typical case on these machines where when you go into switch test, the optos and everything will seem to perform just right. No glitching, no intermittent, nothing. And then the minute you start playing a game, they start acting up, which is really annoying, but that's the way it works. So I had to look for trouble elsewhere. So the question was, what else is there that's common to the optos? Because one other thing I didn't mention was, as I was playing games, very rarely, but it actually did kick out a couple of balls from the main ball trough also, not just the guns. So obviously the problem lies in something that is common to all of the optos, and that is the power supply. The optos need 12 volts, run on 12 volts regulated, and that's basically coming from here. Here's a 7812, and it's fused and supplies 12 volts to all of the opto circuits. I went in, I checked the voltage. The voltage was good, the ripple was non-existent. Just for grins, I replaced the smoothing cap over here, and while I was at it, I replaced the regulator too. Put the board back in, ran it, problem was still there, no change. So now I was getting real stumped here because I didn't know what else to look at. I didn't have an easy way to log an analog voltage because if I had logged the output voltage over here, that may have shown me if something was going wrong with it, but I couldn't think of an easy way to do it. So I put my dunce cap back on and I said, well, wait a minute. This regulator, it's a 78 series, it probably needs about 3 volts headroom to be able to generate a good 12 volts at the output. So if the input voltage goes below 15 volts, the output voltage is going to droop too. And if that voltage gets to around 10.5 volts or so, the optos start misbehaving because of the way they're biased. So, where is this voltage coming from? The unregulated 12 volts. Well, the unregulated 12 volts is marked as plus 18 volts to lamp columns. It's actually going to the flash lamps. So here's a supply, an 18 volt supply that powers the flash lamps, and comes from here. Does like 18 volts or so AC fed into this bridge, and then we got approximately 18 volts DC unregulated coming out of here, and that feeds all of the flash lamps, and it also feeds the regulator. So, well, since we're checking components, I went back and I started checking components. It actually has 2 smoothing caps over here, both 15,000 microfarads. I took them out of circuit, measured them. They look good. I looked at the bridge, and that's when I heard bells ringing. As I measured the bridge, one of the diodes was bad. It was open. So what does that mean? That means under normal circumstances, if there isn't too much of a load on the 18 volt line, it'll still put out, with these 2 massive caps over here, it'll still put out close enough to 18 volts, which is more than enough to drive the 12 volt regulator. But then after watching things, I finally found a correspondence between misbehavior of the machine and what was happening is, when you were in special modes, multi-ball modes, those were getting announced, especially when they started, all the flasher lamps were going off. When all the flasher lamps were going off, it was drawing plenty of current from over here. And what I'm guessing is with the missing diode over here, which was open, this was unable to supply enough current, and this voltage must have drooped below 15 volts. When it drooped below 15 volts, the 12 volt regulator was unable to maintain the 12 volt regulated on the outside, on the output, and that caused the optos to misbehave in a seemingly random, well, not seemingly, in a random fashion, because it depended on the individual opto which one went caca and started, intermittently reporting false openings or closures. But this was a total guess again, because as I said, I didn't have a convenient way to log the voltage, to graph this voltage, to look at it. Anyway, that seemed to be a good enough analysis, and figuring out. I mean, there was a direct correspondence between the flash lamps going off and the false balls being fed into the playfield. I mean, I played it, and yes, there was always a lot of flash lamp activity going on when there were bad balls coming out. Since this was clearly defective, I took it out and I replaced it. And you know what? That was the fix. I was now able to play games without any extra balls being kicked out. So here's the culprit. I measured it in circuit originally and it showed as bad, but let's just repeat it with it out of circuit. This is a 30 or a 35 amp bridge. And the way we measure this is, let's see, this offset pin is the plus DC, and the one diagonal from it is the minus DC, and the other two are the AC inputs. So what we do is we hook the negative DC to positive probe. And then try to hold this thing in place. And we measure to the adjacent pins. That one's good. And that one's good. Then we swap leads. And we put the alligator clips on the negative one, on the negative probe, but connect it to the positive input, positive DC input on the bridge. And do the same test. And look at that. It's open. That diode is gone. So after seeing that, it was just a matter of replacing the bridge on the main power driver board, and all seems to be well. So you can see we have a bunch of those on the power driver board. There's two of them over here, another two hiding underneath the heatsink, but our culprit was hiding there. You can see him half obscured by the wires. That is the 18 volt, unregulated 18 volt DC bridge. And I mean, I couldn't really see it on the flashers. I'm sure the flashes were a little dimmer than before when they all went off, but I could not tell the difference. So that didn't really give me any clues, but with all of that done, the machine now seems to work. And as I sometimes complain, it's a royal pain to get this driver board out because it's got a lot of connectors on it. But it sure was worth it. Well, here we are.
Come.
Unfortunately, I won't be playing a game because it plays the Star Trek music throughout everything. And that would get us a copyright strike, so you just have to take my word for that it's working. I have to figure out a way, because I'd love to play the game and record it, but it's just not the same without the music, without the sound. But until I figure out a way, that's it. And that fixed the switch problems. Thanks for watching. Please like, subscribe, share, and comment. And we'll see you next time.